So, what we saw in the last class was to derive the expression for impedance for a mechanism which involves one adsorbed intermediate, okay, that involves electron transfer reaction and an adsorption reaction. So, it is called EAR reaction. So, to quickly refresh your memory, that is P going into Q with an electron transfer and then A in solution adsorbing and releasing an electron. We have written the mass balance equation, we have written the charge balance equation to tell the charge, mass balance equation tells the theta which is the surface coverage of A adsorbed, how that varies with respect to time when the rate constant, concentration in solution etcetera they are varied. And for a set of parameters we show that the current looks like this, that is it increases and then decreases, you can try that, and at different DC potentials if we take impedance spectrum at around 0.1 you get 2 capacitance loop, at 0.3 somewhere here it is a negative slope, it ends up in the negative, and we also discussed what is the meaning of negative impedance. Okay. It does not mean current goes in the opposite direction, it means current decreases when you increase the potential. So, negative differential resistance means if this is the potential, current goes like this, but this is not 0, this is not 0, this has to be some large value, this is all positive and this is also all positive. So, origin is somewhere here, this is time, this is current, this is potential. So, when you have a DC potential going like this, current not DC potential, AC potential going like this, current also goes, but with an opposite phase. Okay. We also saw that this can be represented by a circuit given here. So, you have solution resistance here, you have double layer capacitance here, and this represents the Faradaic impedance. So, one adsorbed intermediate gives us one Maxwell pair with of course, the polarization resistance. We can write similar equations for other variants where you have one adsorbed intermediate here, you have one adsorbed intermediate, you have an adsorbed intermediate with a parallel reaction, you have single adsorbed intermediate, you can represent the Faradaic impedance by the R polarization along with one Maxwell element. It can also be done with the equivalent ladder circuit, equivalent white circuit, that is understood, because this I can replace this circuit with an equivalent set of elements. Of course, I may have to allow for negative values here to get inductive loop, to get negative differential resistance, but this circuit element, number of circuit elements is sufficient, one resistance capacitance along with the resistance or one resistance inductance along with the resistance is sufficient to model this. Now, I want to go to the next example where you have the following reaction, metal goes into metal 3 plus in solution via 2 intermediates here. So, first it loses 1 electron. So, we have a metal, it loses 1 electron, it becomes M adsorbed. So, electron goes in, it still has not gone into solution. This site also loses an electron, becomes M adsorbed. Then one of the M adsorbed loses another electron and it becomes a different species now, that is called M2 adsorbed, that is the second step. Similarly, you can have some with M2 adsorbed, some with M adsorbed. Now, a part of this M2 adsorbed can lose one more electron and go into the solution, that becomes, so it is basically 3 plus ionic form, 2 plus ion and 1 plus ion are on the surface. So, previously we said M goes to M adsorbed goes into solution. So, here we say M goes to M adsorbed, that is one species. So, bare metal is one species, vacant metal, second is M adsorbed, third is M2 plus adsorbed. So, 2 intermediate species are there and of course, the surface is there. We are going to call theta 1 as the fractional surface coverage of M plus adsorbed. So, surface coverage of M plus adsorbed, M2 plus adsorbed and vacant metal, so many moles per square centimeters or atoms per square centimeter, number of sites per square centimeter, that is the total number of sites. So, this will represent as gamma, this is the moles or area occupied by this per unit geometrical area. So, this number of sites divided by the total number of sites gives us theta 1. The fractional surface coverage of M2 plus adsorbed, we call it as theta 2, and the remaining is basically bare metal. So, the fractional surface coverage of bare metal, sometime we write it as theta V, and that is going to be 1 minus theta 1 minus theta 2. So, we can say 30% of the area, that is 0.3 is occupied by metal plus adsorbed, 20% is occupied by metal 2 plus adsorbed at a given condition, remaining 50% is bare metal. Now, bare metal can become M adsorbed as per the scheme that we have given. Once it becomes M adsorbed, it cannot become bare metal again, it is not reversible. Now, whatever is M adsorbed can become M2 plus adsorbed. When M2 plus adsorbed goes into solution, a bare metal becomes available now, whatever is below that gets exposed. Okay. We can write the mass balance equation for this. We have done this before, I would like you to try. First species, it is formed by the first step, and it is consumed by the second step. Correct, M adsorbed is formed by the first step, consumed by the second step. Rate of formation of the first step is K1, and what is the fractional surface coverage of metal? Theta V, but I am going to just write it as theta 1 theta 2 and 1 minus theta 1 minus theta 2. See, theta 1 theta 2 theta V, they have a relationship that some of them have to be 1. So, I can always write one of them in terms of the other. So, previously for example, we just write theta, we did not write theta 1 theta V, we could have done that, that is all right, but we just write theta for the species and 1 minus theta for the vacant site. So, we will do the same thing here. So, first step forms it, second step consumes it, correct. So, this is what we write for the transient equation or mass balance equation for the M adsorbed species. For the second species, can we write it? Theta 2, it is formed by the second step, that is K2, and the fractional surface coverage here is given as M adsorbed, and it is consumed by the third step. So, we have written the mass balance equation. Can we write the charge balance equation? Can we write the Faraday current? Electron is produced by the first, second and third step, 1 electron each. Therefore, we would write total Faraday current, it is going to be Faraday constant multiplied by first step, the rate is given by K1 1 minus theta 1 minus theta 2. It produces an electron, second step also produces an electron, third step also produces an electron. So, we do the following, we write the mass balance equations, we write the charge balance equation, these are transient equations. Third, steady state theta values. Okay. Fourth, linearization of, you can do mass balance equation first, does not matter, linearization of charge balance equation. Mass balance equation, if you linearize, you will get d theta 1 by d E, d theta 2 by d E, that is fairly lengthy, but it is possible to do. Charge balance equation, if you do, you will get IAC in terms of EAC and d theta 1 by d E, d theta 2 by d E, where we have to substitute. I do not expect you to really write that in a paper, you probably are better off writing this is d theta 1 by d E, then substitute it here and then you will get the answer instead of writing in a very lengthy expression. But this is the general procedure we adopt for any reaction. So, we had done the first part, we had done the second part, I would like you to do the steady state expression, get the steady state expression. When you want to get the steady state expression, we have to set this equation to 0, set the second equation to 0 and then call K1 as K1 DC because it is at a given DC potential, K2 DC, K3 DC, theta 1 as steady state, theta 2 as steady state. So, set this to 0, replace K1 with K1 DC, K2 with K2 DC, K3 with K3 DC. By the way, K1, K2, K3 they all depend on potential, they are all electrochemical steps. You would get two equations in two unknowns, linear equations. So, you can solve them. Do you get equation like this? First equation has to be K1 dc plus K2 dc theta 1 ss plus K1 dc theta 2 ss equal to K1 dc after rearranging it. Second equation is lot easier, that is in the form of A theta 1 ss plus B theta 2 ss equal to C, D theta 1 ss plus E theta 2 ss equal to F. I am just writing it as a dummy variable, its F is not the Faraday constant. So, this is two equations, two unknowns. You can write the expression for this. If I get three variables, as long as it is linear, you should be able to write three equations, three unknowns, five equations, five unknowns, any number of intermediates. You should be able to write it in a matrix form and say theoretically you can invert the matrix and get the solution. You can write it as a matrix form Ax equal to B, where A is a matrix, X is the unknown vector, B is a vector. You can invert it, Gauss elimination, variety of methods are possible. You can get an answer like this, and I can rewrite it slightly differently. Think of it as K1 is the rate of consumption of metal side, K2 is the rate of consumption of metal plus adsorbed, K3 is the rate of consumption of metal 2 plus adsorbed. It is not the rate, it is the rate constant corresponding to that. Inverse of K1 is telling you how slow that is getting consumed, inverse of K2 tells you how slowly M plus adsorbed is consumed, inverse of K3 tells you how slowly M2 plus adsorbed is consumed. So, 1 by K2 tells you how slowly this is consumed, and sum of all this 1 by K1, 1 by K2, 1 by K3 can come in the denominator. This tells relatively how slowly theta 1 or M plus adsorbed is consumed compared to other species consumption rate. But this shortcut may not work in all cases. You can look at this equation and say 1 by K1, 1 by K2, 1 by K3, fractional surface coverage of M adsorbed is going to be 1 by K1 divided by 1 by Ki, sum of all these things. For this M adsorbed it is going to be 1 by K2, in the denominator you get the sum of all these things. This shortcut works in some cases, at least this is one way to check whether you have got it correctly for simple cases.
So, should it be K2 DC or K3 DC?
This should be DC, correct. All these things should have a subscript of DC for each of this case. I missed them, thanks. If we have two species here in some reaction, you will have theta 1, theta 2 possibly, then it becomes a nonlinear equation. In all these cases you will get a solution. Some cases when you have nonlinear equation you will get multiple solution. So, that is a special case. If time permits we will see an example like that. But generally if you have linear equations you will definitely get only one solution, unique solution, and theta value will fall between 0 to 1 for all of these. If you have nonlinear equation, many times even then you will get one physically meaningful solution where all thetas fall between 0 to 1. Some of them may have theta going below 0 or above 1 or come out as a complex number, in which case it is not physically meaningful. You can throw away those solutions. Only the solutions where theta, all thetas have values between 0 to 1 are valid solutions. We are going to see only simple cases, so they will definitely fall between 0 to 1. Okay. We got this part correctly. I think core has not completed. If you are given a little more time, you will be able to get this. Linearization of charge balance equation and linearization of mass balance equation. So, let us try the mass balance equation and see if you can linearize them. Mass balance equation look like this: gamma d theta 1 by dt equal to K1 1 minus theta 1 minus theta 2 minus K2 theta 1 It is the first mass balance equation. So, here we are going to write K 1 as K 1 dc 1 plus B 1 EAC, and that is an approximation. Similarly, we will write for K 2 and K 3. Likewise, theta 1 will write approximately equal to theta 1 SS plus d theta 1 by d E EAC. Similarly, we write theta 2 is theta 2 steady state plus d theta 1 by d theta 2 by d EAC. So, we have 3 rate constants, 2 surface coverages. The third surface coverage is of course going to be written as 1 minus theta 1 minus theta 2. So, we just leave it as it is. I want to take the first equation, rewrite it. Second equation, expand in Taylor series, truncate it after the first term and then get the expression. So, the top expression gamma d theta 1 by dt, we always write it as gamma d theta 1 by dE into dE by dt, and that we know it is not approximately, it is exactly equal to j omega gamma d theta 1 by dE multiplied by EAC. So, I want to take the first equation, write it, we will expand it, rearrange it. Second equation we will write it, expand it, truncate it and rearrange it. So, first equation, left hand side I have written it here. Right hand side you have 2 terms there. First term will give me first term when I write K 1 and when I expand the theta 1 and do all the calculations, I would get 4 terms there. One is a constant independent of EAC, 2 terms will depend on EAC, 1 term will depend on EAC square, and expansion of the first term after expanding in Taylor series, truncating it and then multiplying it, throwing away the EAC square term, you should get 3 terms out of that. Again, it will take you some time, but it is not going to be difficult in terms of complexity. It is lengthy, but it is not something beyond your capacity or beyond your ability to get this. All that you need to do is substitute it, carefully do the multiplication and throw away the terms which are higher order than EAC. Is the first term coming correctly? Have I written it correctly? Second term is going to be of course, it is going to come with a negative sign in front. So, I am just going to put that in bracket. And I have to remember to put the correct subscript here, d theta 1 not steady state, d theta 1 by d E EAC square, and this I will throw away. So, you have to expand it and write it. Because I am little familiar with this, I am able to write it without going through the detailed calculation, but when you practice it, you would be able to do it without any problem.
So, theta 2 is K2 DC, theta 2 is.
No. Please check what is the equation K2 theta 1. So, yes, you have to do it with care, but it should not be difficult. Then when I take the first equation, I recognize the constant terms if I combine them together, they will go to 0. First term gives you a constant term, second term gives you a constant term on the right hand side. They will go to 0 because that is the definition of theta 1 SS and theta 2 SS in fact. Do you follow? Okay. So, that means I can rewrite it and say j omega gamma d theta 1 by dE. EAC is there, I can divide by EAC throughout this. So, after rearranging I should get something like this. On the left hand side I am left with this, I am dividing by EAC throughout this. So, I will not have EAC here. On the right hand side I will combine all the terms that are relevant for d theta 1 by dE, I will group all the terms relevant for d theta 2 by dE, whatever is remaining I will write them, and this is what is remaining here. I can bring this to the left side, I will get k 1 dC plus k 2 dC plus j omega gamma d theta 1 by dE. I can bring this to the left side, that becomes, actually I am sorry, this is k 1 dC, correct, because this has come from k 1 1 minus theta 1 minus theta 2, from that only we got d theta 2 by dE. So, this comes to the left side, it becomes k 1 dC d theta 2 by dE. What remains on the right side, I can keep it as it is, or I can recognize the terms within the square here are equal to the terms in the square here, and then make it in a little simpler form. It is not necessary, it just when you write it, it is easier, when you do the calculation it will not matter, you can keep it as it is. If you are done with the first part, please proceed with the second equation. Now, I will pause here, any of your doubts here? Okay. Go to the second equation. So, this equation when you write it, it looks like and the second equation is also going to look like that, of course different terms. Which you can solve, it is again two unknowns, two equations, linear equations, you can solve and get the answer. Second equation is so we have written this part, and A is this term here, B is this term here, C is this term here. We want to write similarly for this. My claim is it is going to be D here, E here and F here, but we will just write it and confirm that this is correct. But once you get in this form, you realize you can solve for d theta 1 by dE, d theta 2 by dE. There are two simultaneous equations, you have to solve them and get the answer. It is not like what you have done in the one adsorbed species, you can just rearrange and get the answer, because it is one equation, one unknown, just rearrangement would give you. Even if you had 10 equations, 10 unknowns, you can solve them, as long as you recognize that you have to solve them simultaneously. You can't just get d theta 1 by dE equal to something in the first simplification. On the left side you are going to get j omega gamma d theta 2 by, I am sorry, this is d theta 2 by dt, right, going to get d theta 2 by dE EAC on the left hand side. Right hand side, first term is going to give you k 2 dC theta 1 SS plus B 2 k 2 dC theta 1 SS EAC plus k 2 dC d theta 1 by dE EAC So, it is going to give us 4 terms, out of which we will retain 3. Second, similarly we are going to do k3 dc theta 2 ss plus b3 k3 dc d theta 2 by d e EAC plus k3 dc d, I am sorry, this is going to be theta 2 ss, this is going to be d theta 2 by d e EAC plus b3 k3 dc d theta 2 by d e EAC square, out of which the fourth term will go to 0. So, first term k2 theta 1 gives you 4 different terms, second term minus k3 theta 2 gives you 4 different terms. We throw away EAC square term in each of this. The constant term minus constant term will go to 0, that is because k2 dc theta 1 ss minus k3 dc theta 2 ss equal to 0. That is how we in fact get the theta ss values. When the transient is 0, you get steady state values. So, k2 dc theta 1 ss minus k3 dc theta 2 ss is automatically 0. So, you have EAC here, EAC here, EAC here, EAC here, EAC here, divide by EAC and rearrange. This k2 will become minus k2. This is gone. This term here remains on the right side. This is not brought to the left. This term here remains on the right side. This term is brought to the left, it becomes k3 dc. This j omega gamma is for d theta 2 by d e. So, you get one expression here, another expression here, and on the right side we have this term and this term, where I can recognize again k2 dc theta 1 ss is equal to k3 dc theta 2 ss. Therefore, I can simplify it a little bit. Even if I do not simplify and leave it as it is, it is fine. So, please try and derive the expression rather than relying on me to do it correctly and show you the result. My intention is to show you the correct result, but I could make mistakes. Just to avoid the confusion, this E is not potential. This can be written as two equations to unknowns. This is a function of omega, here this is a function of omega. The second equation j omega gamma will come there. If I have many intermediate species, I will get expressions like this. Instead of this, I will get d theta 1 by d e, d theta 2 by d e, d theta 3 by d e and so on. I will have n number of equations, because for each species I have a mass balance equation, and the diagonal will contain omega term there. So, it will come like a matrix. It is going to be d theta 1 by d e, d theta 2 by d e, d theta I by d e equal to, on the right hand side you will have the same length of vector. Here you will get n by n, this is going to be n by 1, it is going to be n by 1 vector here. If you have n species, and the diagonal elements will always have omega. This matrix will always be linear, as long as we assume that truncation is okay, as long as we assume that linearization is okay. The steady state equation you may get non-linear terms. Here you will not get non-linear terms, you will get only linear equation. You can invert it and solve it, you can solve it in whichever way. Now, I am going to assume that if you are given some more time, you will be able to get this. It is not necessary to write d theta 1 by dE, d theta 2 by dE in analytical expression here if you have complicated mechanism and you have many intermediate species. You can just say I will solve it together and give it to a program and solve it. As long as the program can handle complex numbers, you will get the answers correctly. Here I have written it just to show it is possible to do, and also to note that this has come with a product here, right. It is some constant j omega gamma, another constant j omega gamma plus some constant. In the denominator you have a square term for omega. Here also in the denominator you have a square term in terms of omega. If I write it in zeros and poles, I should be able to write d theta 1 by dE as something here. I will have P1, P2 for the poles. Sometimes this is referred to as second order dynamics. That means this equation can have two poles, this equation can have two poles, they may be identical, they may be different, that is all okay, depends on the kinetic parameter values at a given DC potential, but it is possible for you to get a second order term here. It will give you 2 time constant. That means previously we said if it is a simple straightforward reaction with no intermediate species, you will get a semicircle in the Nyquist plot. This is the imaginary, set real. If it is one adsorbed intermediate, we know we can give something like this, we know it can give something like this, we know it can even go back depending on the mechanism. So, it means one more loop is possible, one more time constant is possible, RC is a time constant. If 2 time constants are possible, that means this is possible. This is possible. This is possible. Not with this mechanism will not go back here, but in general 2 time constant means this is possible. This particular mechanism definitely can give rise to first capacitance come because of AA capacitance, 2 inductive loops, one inductive, one capacitance, where inductive loops comes at the end and capacitance comes before, or inductive loops comes first and then capacitance comes later, or 2 capacitances. All these combinations are possible. 1, 2, 3, 4 are definitely possible, and we will show examples where it is possible. So, we can get expression for d theta 1 by dE, d theta 2 by dE. We can expand the Faraday current, which is this is the general expression for Faraday current here. Now, I can expand K1 in K1 DC plus B1 EAC, K2, K3, theta 1 and theta 2, expand it, get in Taylor series, truncate it, multiply, throw away all the EAC square terms, group all the constant terms. So, I will get it as IDC plus IAC, where IDC is going to be same expression, but with the DC . So, this expression will not have any EAC. All the expressions which have EAC can be grouped together, and I am going to claim that it is going to come like this. This will give you B1 K1 1 minus theta 1 minus theta 2 SS, second will give you B2 K2 theta 1 SS, third will give you B3 K3 DC theta 2 SS, and all the theta terms here, when you take the derivative, they will give you a variety of terms, but you can group them and then say d theta 1 by dE, d theta 2 by dE. If you group them and then say here I am going to substitute for this d theta 1 by dE and d theta 2 by dE from the answers I got from the previous expressions. So, mass balance equation gives us the expression for d theta 1 by dE and d theta 2 by dE. I will stop here, we will continue tomorrow. Okay, so yesterday we saw the derivation of equations for reaction with two adsorbed intermediates, right. So, we will say a few more words about certain equations there, what the implications are, and then move on to another type of mechanism called catalytic mechanism. So, we have seen this before, that you can get the expression for this particular reaction, metal going to metal adsorbed going to metal 2 plus adsorbed, and that going into solution in the third step. You can get an expression for d theta 1 by dE, d theta 2 by dE, where theta 1, theta 2 correspond to fractional surface coverage of metal 2 plus adsorbed, metal adsorbed, and they come in the second order in the denominator. You can write the equation for Faraday current, expand it, and you can get the expression for IF AC, IF DC, and you can write this as the ratio of EAC by IAC, here IFAC, that is going to be Faradic impedance. And then you would say if you have a solution resistance, actually this is derived assuming solution resistance is not significant. Okay. So, as long as it is small, it is fine. You have a double layer capacitance, you have the Faradic impedance, substitute for ZF here, whatever the double layer capacitance is, you substitute for that, you can get the total impedance. Because it comes with omega terms in the denominator with product of omega, so you get omega square. This can be modeled using a circuit like this. I am going to say this is 2 Maxwell element with capacitor based circuit. This is going to be Rp, this you can denote as R1 C1 or 2 C2. Likewise, you can replace this C with L, as long as we recognize that it can be positive or negative, it does not matter, replace the C with L. Similarly, you can write this in terms of a ladder circuit. So, you will again have the same number of elements, 2 capacitors, 3 resistors, arranged in a different manner, that is all. So, obviously, the values of capacitance will change when you move from one to another. All these things represent the Faradic impedance only. The double layer capacitance is in parallel to the Faradic impedance, and the resistance, solution resistance is in series to this pair of elements here. Okay. Now, this, what is the value of R1, what is the value of C1, R2, C2, they are related to the kinetic parameters. Okay. They are related to the K10, B1, K20, B2, K30, B3, gamma, and the DC potential at which this is held, because K1 DC, K2 DC etc. will vary with DC. So, you can write R1, C1, R2, C2, Rp, these 5 elements here in terms of 7 kinetic parameters and 1 DC potential. Now, if you take impedance at one potential, DC potential only, let us say you get a spectrum comes like this, you recognize that this can be modeled using a circuit with solution resistance, double layer capacitance, and ZF model like this. So, you can use a circuit with 2 Maxwell elements, one polarization resistance, one solution resistance, and one double layer capacitance. Okay. Now, basically how many points do you need to get the value of all the parameters here? You need 7 points, 2 points corresponding to 2 parameters of CDL and R solution, 5 points corresponding to the 5 parameters here. If you have 2 unknowns, you need minimum of 2 points to solve, right. If you have 5 unknowns in the Faradic impedance, you need 5 points. Okay. Of course, one additional point for solution resistance and one additional point for double layer capacitance. So, that is absolute minimum number of points you need, but you also recognize using the kinetic expression, even if I give you the DC value EDC, you have 7 kinetic parameters mapped to 5 electrical elements. So, I will not get a unique solution for kinetic parameters if I take only one spectrum and then try fitting all the parameters. I can get multiple solutions, I will get in theory I will get infinite number of solutions. If it is a linear equation, linear set of equations, 3 equations, 3 unknowns, you can solve. 2 equations, 3 unknowns, software will tell you that the rank of the matrix is less than 3. So, you cannot solve it. When you get nonlinear equation, by and large you have to give an initial value and it will solve, it will come to some local minimum and then say this is the solution. So, you will not know that there is a problem. So, this is something that you will have to think before you actually work and get the solution. When I give you kinetic parameters and ask you to calculate the impedance, which is what you have been doing so far, it is okay. It is like giving you an equation, I can give you an equation, quadratic equation, I can give you one x value and ask you to give me the one y value. As long as I give you ABC, you can get it. But if I give you one pair of x and y and ask you to get ABC, you will tell me that no, this is not sufficient, you need to give me 3 pairs. Okay. So, likewise here we have 7 kinetic parameters mapped to 5 electrical elements. If I want to get 7 kinetic parameters, I need at least 2 DC potentials at which I have to get the impedance values. So, what would happen is at one DC potential I will get 5 elements here, as long as I have. Okay. So, there are a couple of aspects to this. One, I need minimum 5 points, I can give 100 points here, as long as I fit it to this circuit CDL and our solution. I need absolute minimum of 7 points, I can give many points, many more points, I will still get only 5 elements out of this, 5 elements for ZF and 2 elements for the R solution and CDL. So, by giving more number of points at one EDC, I will not be able to get unique value for K1, B1, K2, B2, etc. So, you can't just look at the total number of parameters and then say I have 7 parameters for kinetics, 1 parameter for CDL, 1 parameter for solution resistance, therefore, I have 9 parameters in total. If I give 100 points, I can do the regression and get the solution. That is not correct. Maybe I will give more concrete example later. What I have done is taken that equation, given different set of kinetic parameter values and chosen certain DC values and created the spectra. You can see one capacitive loop and 2 inductive loops here, one capacitive loop, another capacitive loop with inductive loop. This is the first one, second one. Third one, I got 1, 2, 3 capacitive loops. Fourth one, I got capacitive, inductive and capacitive. This is just to say that all these things are possible. Okay. If I change the DC potential here, spectrum may continue to show the same shape or it may be different. Okay. I have not really spent lot of time, I do not know if it is possible for one set of kinetic parameters with different DC potential to give all 4 spectrum at different potentials, maybe not necessarily for this particular mechanism. If I make some variations to this mechanism and add some more kinetic parameter, it may be easier to do. I have not tried that, but the idea is if you have 2 adsorbed intermediates, it is possible for you to generate 2 capacitance or 1 capacitance and 1 inductance or 2 inductance in whichever order, higher frequency, lower frequency range where it manifests itself, and this is apart from the first capacitive loop you get at high frequency for double layer capacitance and charge transfer resistance. Okay. So, we saw that we can use this circuit, it is just that this is going to be our solution CDL, this is RP in this representation. You can come up with other variants. this is just one example. This is what we have seen before, this is the next variant where I can say first step is reversible, second step is reversible. In all these cases, of course, if we really take it near the equilibrium potential, these have to be reversible. What you assumed is this irreversible, meaning probably it is little away from the equilibrium and the reverse reaction can be neglected. Third one, look at this, in the original equation we have said M2 plus adsorbed goes into M3 plus and solution. So, in solution it is charged with 3 plus, whereas here just M2 plus adsorbed goes into solution. So, this is not just take this mechanism and make it reversible. First and second step look similar, but the third step is actually different. Okay. Third step is a chemical step, it does not involve electron transfer, therefore, K3 is independent of potential. Another way to say that is B3 is 0. So, what would happen is current equation will be different. Of course, even the mass balance equation will be different because the reverse reactions are not taken into account, but this is one variant. You can come up with multiple variants of this mechanism to tell that okay, maybe this reversible I have to take into account. Of course, you need to have some idea about the actual chemical reaction, overall reaction. If you think it is Fe going to Fe 3 plus, you have to come up with this or some variation where in solution it is 3 plus. If you think it is a reaction of Cu going to solution as CuSO4, then you can't use the 3 plus because we know that Cu does not exist in 3 plus oxidation state. So, it has to be based on some idea about what is supposed to be present in the solution phase. Okay. But what you know here is, for example, M going to M3 plus solution plus 3 electron, if this is the overall reaction, you can come up with this mechanism. If the reaction is reversible or irreversible, then you can come up with this mechanism or another variant where you can say this goes via intermediate, in addition it can directly go in parallel, all those things are possible.